All right, so as I was racing to put together this study guide for you from the questions from the quiz without their answers, without the multiple choice answers, I messed up a little bit. This doesn't make any sense when you read it. Two identical planets orbit a star, compare their orbital radii. We don't know anything, so we can't. So what I did was I cut and pasted, or I grabbed, this is what actually was on the quiz right here. Two identical planets orbit a star. Concentric. Concentric means having the same center. All right, so if I have a center right here, and then I put a couple of circles, if I start at the same point, these are concentric, meaning they have the same center. So if two stars or two planets are in concentric orbits, it just means they're orbiting central gravitational mass the same way we've been talking about, in a way that's consistent with what we would expect. Okay, so that's what concentric means. All right, so these are the choices that were given to you on the quiz, and let's see if we can make some sense out of these. If we have, messing around here too much. All right, if we have two identical planets, concentric orbits, of the two, the planet that is farther from the star, okay? The planet that is farther. So we will call that planet F, okay? And then we have planet N for planet near. All right, so F is for far, N is for near. Okay? All right, so for the one that's farther from the star, does it have a smaller period? Well, let's ask ourselves, does that make sense? That means that if it has a smaller period, it takes less time to go around the circle. That means it's faster. All right, so does the planet that's farther have a faster orbit? Let's check that in a second. Does it have a greater period? In other words, is it moving slower if it's farther away? Does it have a smaller gravitational mass just because it's farther away? That doesn't make any sense at all. We can't even consider that one. Can we make any conclusion suggesting that a planet that's farther from a star have a smaller mass? No. Less gravitational force, but not smaller gravitational mass. We don't know anything about the gravitational mass of the planet based on its distance. Those are independent. You can tell because if you've got the sun, we've got Mercury and Venus getting bigger, Earth slightly bigger, Mars smaller, than Jupiter real big. So the sizes get up, go down, get bigger and smaller. It doesn't make any sense. We can't draw any conclusions about the size of the planet based on its distance from the sun. And larger universal gravitational constant, geez, what's wrong with that? A larger constant. That doesn't make any sense. So we'll get rid of that one as well. So basically the question we're asking is, which one has a faster orbit? The one that's closer or the one that's farther? All right, well, we can easily determine what's going on there because we remember, as we've been doing for almost everything in this unit, we're saying that centripetal force is supplied by gravity, that the centripetal force is equal to the gravitational force because that's where it comes from. How much force do we need? Where does it come from? All right, so we're dealing here, it asks about period, so we'll use the one that has period as its indication of speed, okay? So we'll use the version of centripetal force that has period as the indication of speed, which means that we will use m times 4 pi squared r over t squared is going to be equal to universal gravitation, g, big M, little m, over r squared, all right? By now, this ought to look real familiar. All right, our masses are going to cancel. All right, so what is our technique for doing this? We're trying to relate speed and period. So let's get them on either on the same side or as one constant of proportionality to another. All right. So let's look at getting them as a ratio. This is what we did before when we put all the variables on one side and all the constants on the other. So we end up with r cubed over t squared is equal to gm over 4 pi squared, which is constant, okay? This is constant. This law, this is Kepler's law, we just learned that. This is sometimes called the harmonic law or the law of harmonies because there's a relationship between distance and speed. All right, so if we know that this is true, that means that r cubed for the near planet over t squared for the near planet has got to be equal to, and since we're trying to solve for the farther planet, we'll put that on the left-hand side. We'll say r farther cubed over t farther squared. So we're trying to find the relative speeds. All right, well, if this is true, well, they put an equal mark. If this is true, can you understand that if we just invert it, that would be true as well? Or we could just run through it here. We cross multiply and get TF times Rn cubed is equal to Tn times Rf cubed. And then we end up with T farther squared is going to be equal to T nearer squared times what? T nearer times Rf, R farther. All right, we're interrupted by an announcement there. All right, so we have R farther over R near cubed. All right, so we know that T farther is equal to T nearer times radius farther over radius nearer to the 3/2. The exponent doesn't matter really, because all we really need to know is the ratio of what's inside here. All right, in other words, we could see that if this right here is greater than 1, then T farther is greater, right? If this is greater than 1, which it is because farther is going to have a greater radius, right? R farther is greater than R nearer, which means that R farther over R nearer is greater than 1. So if we're multiplying this, our given initial period times a number that's greater than 1, then this over here on this side is going to be greater than this, okay? So T farther is greater than T nearer. That's what we would expect. We know that the farther something is out and away, here's the sun. A year is shorter for Mercury than it is for, not to scale, for Jupiter, not only because the orbit is bigger, but because Mercury literally moves around faster than Jupiter does in its orbit. And if you remember that animation that I gave you the link to, you can look at that and see the differences in their speeds.